Hello and welcome. In this video, we're going to walk through a set of practice SAT math problems. By the end of this session, you will be able to apply various mathematical concepts to solve a range of problem types, from algebra and geometry to number properties. Our goal is not just to get the right answer, but to understand the logic behind the solution. So let's dive into our first problem. Problem 8 presents a word problem about baseball cards. We have two collectors, Andy and Brittany. Let's start by defining our variables. Let's use A for the number of cards Andy has and B for the number of cards Brittany has. These are their original collections. The problem describes a transaction. Andy gives Brittany 8 cards in exchange for 1. First, consider the exchange. Andy gives up 8 cards and gains 1, so his collection decreases by 7 cards overall. Brittany receives 8 cards and gives up 1, so her collection increases by 7 cards. After this exchange, Andy's new card count is a -7, and Brittany's new count is B plus 7. The problem states that after this exchange, Andy has 6 more cards than Brittany. We can write this as an equation. Andy's new total equals Brittany's new total plus 6. Now, we just need to solve this equation for A to find the relationship between A and B. Let's simplify the right side first. 7 plus 6 is 13. Next, to isolate A, we add 7 to both sides of the equation. This gives us A equals B plus 20. So, the original number of cards Andy had, A, is 20 more than the original number of cards Brittany had, B. This corresponds to answer choice D. We successfully translated the word problem into an algebraic equation and solved it to find the relationship between A and B. Moving on to problem 9, we are asked to find the value of x that satisfies this rational equation. Our equation is x squared minus 9, divided by the quantity x plus 3 times the quantity x plus 5 equals 2. The first thing we should always look for is a way to simplify. Notice the numerator, x squared minus 9. This is a special form called a difference of squares. The difference of squares formula states that a squared minus b squared equals a minus b times a plus b. Applying this to our numerator, x squared minus 9 becomes x minus 3 times x plus 3. Now we can rewrite our equation with the factored numerator. This is x minus 3 times x plus 3, all over x plus 3 times x plus 5 equals 2. You can see we have a common factor of x plus 3 in the numerator and denominator. We can cancel this common factor, but it's crucial to remember the original equation's domain. The denominator cannot be 0, which means x cannot equal -3 or -5. So, while we can simplify, we must check our final answer against this condition. After simplifying, we are left with x minus 3 divided by x plus 5 equals 2. To solve for x, we multiply both sides by the denominator x plus 5. This gives us x minus 3 equals 2 times the quantity x plus 5. Now, distribute the 2 on the right side. 2 times x is 2x, and 2 times 5 is 10. The equation becomes x minus 3 equals 2x plus 10. To solve for x, let's get all the x terms on one side and the constants on the other. Subtracting x from both sides gives us -3 equals x plus 10. Then subtracting 10 from both sides gives us -13 equals x. So our solution is x equals -13. Now let's check our domain condition. Is -13 equal to -3 or -5? No, it's not. So -13 is a valid solution. Therefore, the correct answer is C, x equals -13. We successfully simplified a rational expression and solved the resulting linear equation. Problem 10 asks us to find the x-coordinates of the points of intersection for two given functions. Our two functions are f of x equals 6x plus 1, which is a linear function, and g of x equals x squared plus 5x minus 5, which is a quadratic function. To find where two functions intersect, we must find the points where their y values are equal. This means we can set the two equations equal to each other. So we set f of x equal to g of x, which gives us the equation 6x plus 1 equals x squared plus 5x minus 5. We now have a quadratic equation. The standard way to solve a quadratic equation is to get all the terms on one side, set the equation to 0, and then solve. We'll aim for the standard form, x squared plus bx plus c equals 0. Let's move the terms from the left side to the right side. We subtract 6x and subtract 1 from both sides. This leaves us with 0 on the left and x squared minus x minus 6 on the right. Now we need to solve the quadratic equation x squared minus x minus 6 equals 0. We can do this by factoring. We are looking for two numbers that multiply to 6 and add to a 1. The numbers 3 and 2 fit this description perfectly. 3 times 2 is 6, and 3 plus 2 is 1. So we can factor the quadratic into x minus 3 times x plus 2. For the product of two factors to be 0, at least one of them must be 0. So we set each factor equal to 0. Solving the first equation, x minus 3 equals 0, gives us x equals 3. Solving the second equation, x plus 2 equals 0, gives us x equals 2. These are the x-coordinates of the 2 points where the line and the parabola intersect. Therefore, the correct answer is C, with x-coordinates 2 and 3. We have successfully found the intersection points by setting the functions equal and solving the resulting quadratic equation. Problem 11 is a geometry problem involving angles. We need to calculate the value of x based on the provided figure. Let's first analyze the diagram. We have a horizontal line and a vertical line forming a coordinate-like plane. The square symbol in the upper left corner confirms they are perpendicular, creating 90-degree angles. There is a third line passing through the origin. In the lower left quadrant, the angle between the vertical axis and this third line is labeled x degrees. In the upper right quadrant, the angle between the horizontal axis and the line is split into two angles, labeled x plus 10 degrees and x 10 degrees. The key to solving this problem lies in understanding two fundamental geometry concepts: vertical angles and complementary angles. First, the angle x degrees and the angle formed by the third line and the horizontal axis in the lower right quadrant are vertical angles. Vertical angles are always equal, so that angle is also x degrees. Now let's focus on the upper right quadrant. We know the angle between the horizontal axis and the vertical axis is 90 degrees. This means the angles inside this quadrant are complementary. They add up to 90 degrees. So, we can set up an equation by adding these three angles together and setting the sum equal to 90. The equation is x plus the quantity x plus 10 plus the quantity x minus 10 equals 90. Now we can simplify and solve for x. Notice that we have a plus 10 and a minus 10, which cancel each other out. This leaves us with x, which simplifies to 3x, so 3x equals 90. To find x, we divide both sides by 3. 90 divided by 3 is 30. Therefore, x equals 30 degrees. Let's quickly check this. The three angles in the upper right quadrant would be 30, 30 pi plus 10 to 40, and 30 pi to 10 to 20. Adding them up, 30 plus 40 plus 20 equals 90, which is correct. The answer is A, 30 degrees. Problem 12. Tests our understanding of exponent and square root rules. We need to simplify the given expression. The expression is a to the power of negative 3 times b to the power of negative 1, all multiplied by 81 a squared b to the fourth, raised to the power of 0.5. Let's tackle this step by step. First, let's simplify the term in parentheses. We need to distribute the power of 0.5 to each factor inside the parentheses. Remember, raising something to the power of 0.5 is the same as taking its square root. So this becomes the square root of 81 times the squared raised to the power of 0.5 times b to the fourth raised to the power of 0.5. The square root of 81 is 9. For the variable terms, we multiply the exponents. So a squared raised to the 0.5 is a to the power of 2 times 0.5, which is a to the first. And b to the fourth raised to the 0.5 is b to the power of 4 times 0.5, which is b squared. So the second part of our expression simplifies to 9a squared b squared. Now we can multiply this back by the first part of the expression. This gives us a to the negative 3 times b to the negative 1 times 9a squared b squared. To multiply terms with the same base, we add their exponents. Let's group the terms with the same base. This rearranges to 9 times a to the power of negative 3 plus 1 times b to the power of negative 1 plus 2. Adding the exponents, we get a to the power of negative 2 and b to the power of 1. The simplified expression is 9a to the negative 2, b. This expression is now fully simplified. We applied the rules for exponents and square roots systematically. Looking at our options, this matches answer choice D. The key was to simplify the parentheses first and then combine like bases by adding exponents. Problem 13 is a concept question based on the combined gas laws. It asks what to do to car tires in the winter. The problem gives us the combined gas law, P times V, divided by T equals a constant. Here, P is pressure, V is volume, and T is absolute temperature. Let's analyze the relationship between temperature and pressure based on this formula. If we assume the volume of the tire is constant, we can rewrite the law as P over T equals a constant. This shows a direct relationship. For the ratio P over T to remain constant as one changes, the other must change proportionally. This means if temperature goes down, pressure must also go down. So in the winter, the temperature decreases. According to the gas law, this will cause the pressure inside the tire to decrease. The problem asks what we need to do to maintain the correct tire pressure. Since the pressure has decreased, we need to increase it to get it back to the prescribed value. Therefore, we must inflate the tires. This makes intuitive sense. Cold weather causes the air inside your tires to contract and exert less force on the walls of the tire. So, the correct answer is D. Inflate the tires to correct pressure. This is a great example of how physics principles can be applied to an everyday situation. Problem 14 is about polynomials. We are given an equation that equates a product of two linear binomials with a standard quadratic form. The equation is the quantity 2x minus 7 times the quantity 8 minus 3x equals a x squared plus bx plus c. We need to find the value of a plus b plus c. Let's start by expanding the left side of the equation. We can use the FOIL method, which stands for first, outer, inner, last. First, we multiply the first terms. 2 times 8 is 16. Outer, we multiply the outer terms. 2x times negative 3x is negative 6 squared. Inner, we multiply the inner terms. Negative 7 times 8 is negative 56. Last, we multiply the last terms. Negative 7 times negative 3x is positive 21x. Now we add these four terms together to get the expanded polynomial. 16x minus 6 squared minus 56 plus 21. Next, we combine the like terms, which are the x terms. 16x plus 21x equals 37x. Rearranging into standard quadratic form, we get negative 6x squared plus 37x minus 56. Now we can equate this to the standard form x squared plus bx plus c. By comparing the coefficients, we can find the values of a, b, and c. The coefficient of x squared is a, which is 6. The coefficient of x is b, which is 37. And the constant term is c, which is 56. The problem asks for a plus b plus c. We just substitute our values. 6 plus 37 plus negative 56. This simplifies to 31 minus 56, which is 25. So the value of a plus b plus c is 25, which corresponds to answer choice A. We successfully expanded a product of binomials and then added the coefficients of the resulting quadratic. Problem 15 deals with complex numbers. We need to simplify a quotient of two complex numbers and express it in the form x plus ye. The expression is 5 plus 2i divided by 4 minus 3i equals x plus y. The key to simplifying a quotient of complex numbers is to multiply the numerator and the denominator by the complex conjugate of the denominator. This eliminates the imaginary part from the denominator. The denominator is 4 minus 3i. Its complex conjugate is 4 plus 3i. We multiply both the numerator and the denominator by this conjugate. Let's first calculate the new denominator using the FOIL method. First, 4 times 4 is 16. Outer, 4 times 3i is 12i. Inner, negative 3i times 4 is negative 12i. Last, negative 3i times 3i is negative 9i squared. The middle terms, 12i and 12i, cancel out. The I squared term simplifies to what 1, so negative 9i squared becomes negative 9 times 1, which is positive 9. Our denominator is 16 plus 9, which is 25. Now let's expand the numerator, again using the FOIL method. First, 5 times 4 is 20. Outer, 5 times 3i is 15i. Inner, 2i times 4 is 8i last. 2i times 3i is 6i squared. Combine like terms. The I terms add up to 23i. The 6i squared term becomes 6 times 1, which is 6. The numerator simplifies to 20 plus 23i minus 6, or 14 plus 23. Now we put the new numerator and denominator together. The simplified fraction is 14 plus 23i all over 25. To express this in x plus y form, we split the fraction into its real and imaginary parts. This gives us 14 over 25 for the real part, and 23 over 25i for the imaginary part. By comparing this to x plus y, we find that x equals 14 over 25 and y equals 23 over 25. This corresponds to answer choice C. By multiplying by the complex conjugate, we successfully simplified the expression and identified its real and imaginary components. Problem 16 is a set theory or Venn diagram problem, often solved using the principle of inclusion-exclusion. We have a music class, and students must sign up for at least one instrument. This means every student is in one of our categories. We have two categories, guitar and piano. Let's write down the information given. 17 students signed up for guitar, 9 for piano, and 6 signed up for both guitar and piano. We need to find the total number of students in the class. A great way to visualize this is with a Venn diagram. We draw two overlapping circles, one for guitar and one for piano. The overlapping area represents students who play both. We should always start by filling in the overlap first. This is the most specific information we have. 6 students signed up for both, so we write 6 in the intersection. Now let's find the number of students who play only guitar. The total number of guitar players is 17, but 6 of those 17 also play the piano. So we subtract the overlap from the total. 17 minus 6 is 11. This means 11 students play only the guitar. We write 11 in the guitar circle outside the overlap. We do the same for the piano players. The total is 9 and 6 of them play both. So 9 minus 6 is 3. 3 students play only the piano. We write 3 in the piano circle outside the overlap. The question asks for the total number of students in the class. Since every student signed up for at least one instrument, the total number of students is the sum of those in the diagram. We add the number of students who play only guitar, only piano, and both. 11 plus 3 plus 6 equals 20. There are 20 students in the class. Problem 17 is a system of equations, and we need to evaluate an algebraic expression. We are given two equations, equals 3 plus n, and n equals 4 minus m. We need to find the value of m squared minus n squared. There are two main ways to solve this. The first is substitution. We can substitute the first equation, m equals 3 plus n, into the second equation for m. This gives us n equals 4 minus the quantity 3 plus n. Simplifying, we get n equals 1 minus n. Adding n to both sides gives 2n equals 1, so n equals 1/2. Now we can substitute n equals 1/2 back into the first equation to find mm equals 3 plus 1/2, which is 3.5 or 7/2. Now we evaluate m squared minus n squared. We can use the difference of squares identity. M squared minus n squared equals m minus n times m plus n. Plugging in our values, we get 7/2 minus 1/2 times 7/2 plus 1/2. The first parenthesis is 6 over 2, which is 3. The second is 8 over 2, which is 4, and 3 times 4 is 12. Let's look at the second, more elegant method. This one involves manipulating the original equations. First, let's rearrange the equations to get m and n on one side. From the first equation, m minus n equals 3. From the second, m plus n equals 4. Notice we need to find m squared minus n squared. And remember, m squared minus n squared equals the quantity m minus n times the quantity m plus n. But we just found those exact quantities. From our rearranged equations, m minus n is 3 and m plus n is 4. So m squared minus n squared must equal 3 times 4, which is 12. This method is much faster because it avoids solving for the individual variables. So the value is 12. Problem 18 is a geometry problem involving similar triangles. We are told that triangle ABC is similar to triangle DF. This is the most important piece of information. Similarity means that corresponding sides are in the same proportion and corresponding angles are equal. The order of the letters tells us which vertices correspond. We are given that angle BAC is 90 degrees. Angle DFE is x degrees, AC is 4, BC is 5, and the ratio of sides BC over EF is 15. We need to find AB over DE times the sine of x. Let's first use the similarity property. Since the triangles are similar, the ratio of any pair of corresponding sides is the same. We know the ratio BC over EF is 15. This means that AB over DE must also be 15, and AC over DF must also be 15. All corresponding side ratios are equal. So we found the first part of our expression. AB over DE is 15. Now let's find the sine of x. First, we need to know what angle corresponds to angle DFE. From the similarity statement, the third vertex C corresponds to the third vertex F. So angle DFE corresponds to angle BCA. This means that x is the measure of angle BCA. To find the sine of angle BCA, we need the side lengths of triangle ABC. We know AC is 4, BC is 5, and angle back is 90 degrees. This is a right-angled triangle. We can use the Pythagorean theorem to find the length of the remaining side, AB. AB squared plus 16 equals 25. Subtracting 16 from both sides, AB squared equals 9. Taking the square root, AB equals 3. Now we have all sides of triangle ABC. AB is 3, AC is 4, and BC is 5. We need sine of angle BCA. Remember the SOH-CH-TOA mnemonic for trigonometric ratios. Sine is opposite over hypotenuse. For angle BCA, the opposite side is AB, and the hypotenuse is BC. So, sine of angle BCA is AB over BC, which is 3 over 5. Since x equals angle BCA, sine of x is 3/5. Now we can put it all together to find the expression AB over DE times sine x. We know AB over DE is 15, and sine x is 3/5. So we calculate 15 times 3/5. 15 times 3 over 5 equals 45 over 5, which simplifies to 9. Therefore, the value of the expression is 9. Problem 19 is a statistics problem involving mean and median. 6 teams participated in a contest. 5 of the scores are known, and the last score is x. The scores are 95, 77, 100, 78, 80, and x. We are told that x is the median of the other 5 scores. Let's first find the median of the other 5 scores. To do this, we must arrange them in ascending order. The ordered scores are 77, 80, 95, 100. The median of an odd number of data points is the middle value. In this case, it's the third score. So, the median of the other 5 scores is 80. The problem states that x is this median. Therefore, x equals 80. Now we know all 6 scores. The question asks for the average or mean team score for the entire contest. The 6 scores are 95, 77, 100, 78, 80, and x, which we now know is also 80. The formula for the mean is the sum of the scores divided by the number of scores. So we add all 6 scores together and divide by 6. Adding the scores, we get a total of 510. Dividing by 6 gives us 85. The average score is 85. Problem 20 is a classic geometry problem that combines inscribed figures. The problem can be confusing if you don't draw it out. We have a circle inscribed in a square, and then a second square inscribed in that circle. Let's draw this. First, a large square. Second, a circle inside it that touches all 4 sides. Third, a second, smaller square inside the circle with its vertices on the circle's edge. The side length of the outer square is given as L equals 10. We need to find the area of the inner square. Let's work our way from the outside in. We know the side length of the large square is 10. Let's find the properties of the circle first. Because the circle is inscribed in the square, its diameter must be equal to the side length of the square. So the diameter of our circle is 10. This means its radius is 5. Now let's look at the inner square inscribed in this circle. For a square inscribed in a circle, the diagonal of the square is equal to the diameter of the circle. So the diagonal of our inner square is also 10. Let's call the side length of this inner square S. The diagonal, along with 2 sides of the square, forms a right-angled triangle. We can use the Pythagorean theorem to find the relationship between the side and the diagonal. By the Pythagorean theorem, s squared plus s squared equals the diagonal squared. Substituting the diagonal value, we get 2s squared equals 100. Dividing by 2, we find that s squared is 50. The question asks for the area of the inner square. The area of a square is its side length squared, which is s squared. We just calculated that s squared is 50, so the area of the inner square is 50 square units. That brings us to the end of this walkthrough. We've tackled a variety of challenging SAT math problems, from algebraic manipulations and system of equations to geometry concepts like similar triangles and inscribed figures, and even some statistics and physics. The key takeaway is to approach each problem systematically. Read carefully, identify the core concept, write down what you know, and then apply the relevant formulas and strategies step by step. And always, always double-check your work. I hope this detailed explanation has been helpful. Keep practicing, and you'll build the skills and confidence to succeed. Thanks for watching.